All right, hi everyone. I'm Mohammed. I'm doing my PhD at Bill Kent University. My advisor, John Olakan and Onur Mutlu. Today I'm going to present about enabling fast and accurate read alignment process. And I'm trying my best to hide all technical details about hardware component. So I'm trying to simplify it as much as possible. As you're all aware about the genome analysis steps, starting by sequencer generating like hundreds of millions to billions of short reads, and then unfortunately those reads doesn't have any information about which gene it comes from. So we need to align them to get the full sequence and then do further processes. So there's a problem here. The problem is we have a sequencer, we have a aligner. So the sequencer is able to generate like 300 million of bases per minute, but the aligner is able only to align 0.6% of those reads. And thus, there is a performance bottleneck here, and they cannot cope to each other. So what we are trying to do is to solve this problem and bridge the gap between the sequencer and the aligner. There's a few key observations that help us to solve this problem. The first thing is this alignment process involves like dynamic programming algorithm, which is normally like taking quadratic time, and thus this dynamic programming occupies like 90% of the running time for any current mapper. The second observation is the majority of candidates' location doesn't align, like do not align with the reference due to high dissimilarity. And those like wasting the time verifying them using dynamic programming while they don't align. So we can easily, if we use some simple heuristics, like just to discard them and then let the dynamic programming do the rest on the other candidate location. And more importantly, like we are looking only for a few mismatches, and normally less than 5% of the mismatches. So what are the other researchers doing? The first direction is going to improve the filtering strategies or build the new filtering techniques. And the second direction is to have accelerator, which is normally hardware, as you all know that the hardware is much faster than the CPU or a typical algorithm. And the problem with the filtering techniques, such as Hamming distance or seed filtering, sometimes they are slow or inaccurate. And for hardware accelerator, we have FPGA, GPUs, and CMD. You can see here is the timeline of the current or for the last 2 decades mapper. And you can see only for the last 5 years, start like the hardware accelerator getting more attention. You can see the blue mappers are in FPGA, the red in GPU, and so on. So let's talk a bit about our proposed filters. And what we are trying to do is a filter on FPGA. So we're combining 2 directions, filtering strategies on hardware platform. So here's a typical scenario where we have a sequencer, then the dynamic programming. What we are doing is having multi-layer filtering strategy. And if it is very accurate, we can eliminate the need for the dynamic programming. So I guess the first 2 scenarios where we have exact matching and substitution is very easy and trivial to do it. And for insertion, you can notice, do you have a pointer? Okay. If we have inserted base there, all the trailing bases will be shifted. And thus, if we want to do correct mapping, either you want to shift the read itself or the sequence to one direction so that you can pairwise compare them correctly. Same thing for deletion. If you delete a base, all the trailing bases again will be shifted to one direction, either right or left. And you can think easily about other scenario where you have insertion and deletion in same or substitution also in the same mapping. So here's the first filter. We have first the query and we have a reference segment, all of them same length. And what we are trying to do is having a set of masks. You can see this set. The first mask is responsible for detecting the substitution. So we do just pairwise comparison, which we call it Hamming mask due to the Hamming distance. And then we have a set of deletion mask and insertion mask. And whenever you have long matches, which are highlighted in green, then means that for example, we have this long match and the deletion mask mean there is one deleted base somewhere, and that's why you get the long match here. And what you do basically is you have the AND mask, then you just do AND operation to all those masks, you will get the result here. Then you count how many ones you have at this mask, you will get how many mismatches you have. However, you may get with a problem with this filter, because when you do AND operation, so any 0 in a column will cancel all the ones. So you won't get that there is, for example, here there is a mismatch, but you won't get it because of the AND operation. So this filtering has a problem and has advantages as well. So the first advantage is purely relies on bitwise operation, which is suitable for any hardware platform and very fast to do it, and occupies less resources. We are talking here about FPGA. And the disadvantages, as I said, the false positives. It may the mapping has more mismatches than allowed, but it will let the mapping pass through the filter. And the second disadvantage, we don't have any information here about the type of mismatch, whether insertion or deletion. And as you know, in the dynamic programming, we have backtracking, so we can come up with the exact type of mismatches. The second filter here is we have, again, a set of masks. But rather than doing AND operation, we are trying to attract those long matches to what we call a magnet mask. So this magnet mask try just to attract the long matches as it is, and keeping the number of mismatches in a correct way. So for example, first step is to search for the longest match. We have some long matches, and we have longest of those, for example, which is this one in the second mask. And then we check the length of this match, and should be strictly not less than this equation. This equation, we got it when we have a sequence and you have a bunch of mismatches distributed equally among this read, then it will divide the sequence into equal length of segments. So at the end, when you get each mismatch here, you will have the number of mismatches and transparently in the magnet mask, and then you just can sequential scanning and come up with the number of mismatches exactly. And we iterate this process, extracting the long matches e+1 times, because if you have a sequence, you have a single error in the middle, then it's like dividing the sequence into 2 segments. So that's why e+1 will guarantee that you will collect all the long matches everywhere. This has advantages of multiple layer filtering. Here we are talking about highly integrated layers. So it's not just you have 1 step, 2 steps, 3 steps. They are highly integrated. So for example, when we check this one, if it doesn't satisfy this function, then directly discard this mapping. Don't continue to attract the long matches and so on. And even if it is satisfied, the computation you use to attract that long matches will be used for the next steps. So it's not just adding the steps together. It's highly integrated together. And high accuracy by incorporating long matches awareness. And you can see here we don't have that much of false positives. And can tell you exactly the type of mismatch without backtracking process. So in this filter, you can eliminate the need for dynamic programming. But the disadvantage, of course, the accuracy comes at the cost of occupying more resources. And it's 10% of the chip. And this concern about the parallelism. So you cannot parallelize this design that much. Only you have 10 times or less. OK, now let's talk about a few numbers and experiment. We have compared the two filters using 10 data set from internet. And we have varies the error rate from 1 to 5. You can see that the first filter, which call it Gatekeeper, it has high false positive. It could be up to 50% of the accepted mapping. And for the second filter, it only takes less than 1%. So magnet is very accurate. And for the speed or the runtime of our 2 filters, here without parallelism. So you can see that the Gatekeeper, which is green in the figure in the above, takes like 300 billion mapping per 40 minutes. For the magnet, which is the second filter, takes less time, about 180 mapping per 40 minutes. And one important thing about using hardware here in accelerating the filtering strategies is that when you have, for example, we compare with SSD. SSD is a filter, but implemented on SIMD, or a CPU algorithm. And when we increase the error rate, the runtime will drop easily. You can see at error 5, the runtime is much lesser than at error 1. But for FPGA or hardware, because it's relying on oscillator or clock frequency, so it maintains the same speed of mapping. And this is the very important difference between having a filter or algorithm on FPGA or hardware in general and on CPU. So here is after parallelism. We have our two filters. And here we cannot say which one is better. Both of them are important because one of them is very fast and the other is very accurate. And anyway, we will have like the dynamic programming in the next step. So even Gatekeeper is not accurate. And accuracy here doesn't mean false negative. It just false positive. It has 0 false negative. So if it is a correct mapping, it will keep it. It won't discard it. And this is the speed after parallelism again. We have like 1,500 billion mapping per 40 minutes, and we are occupying 50% of the chip. For the magnet, we have 180 billion only, but it's very accurate. On average, is less than 1% of the accepted mapping. Here's just a brief like a summary about the FPGA for those who doesn't know the FPGA. This is how it looked like. This is Xilinx VC709, which we are using. And this is my last slide. And as you know, the FPGA only accepts binary data. So you need to convert the sequences into binary. Then you process it. And only support bitwise operations. And another concern about maximum throughput, you can transfer from the CPU or the computer to the FPGA in order to process it is limited by 3.3 gigabyte per second. And the other are like just specs for the FPGA. In a summary, the FPGA will likely continue to be the best option for accelerating the algorithm. And it is, so far, is the best among the GPU and CMD. So if you are thinking about accelerator, you can go ahead for FPGA if your algorithm supports bitwise operations. And 2 order of magnitude acceleration worth the cost and design efforts, because FPGA is not simple like writing code, synthesize it, and that's it. It's more complicated than this, but don't worry about it. You will get at the end a high speed out of it. And integrating the FPGA accelerator with the sequencer will hide the complexity of those designs. So as a bioinformatician or a biologist, you don't have to worry about the complexity of FPGA. You just, if it is combined with the sequencer, then you use it as it is. You will get the SAM file or PAM file, and that's it. This is my advisor, co-advisor. Thank you.